So in our last lecture, we set up the mitochondrion. We thought about the different parts of the mitochondria and how we need to move things from the cytosol to the mitochondrion, and then talked about the specific players that we need to move back and forth with ATP, ADP, inorganic phosphate, NADH, and so forth. So what we're going to do in this lecture is actually learn about the 5 complexes really that make up the electron transport and oxidative phosphorylation process. So again, complexes 1, 3, and 4 are responsible for pumping a proton gradient, and then complex 5, also called ATPase, is responsible for utilizing that proton gradient to synthesize ATP. So again, it's important to remember that complexes 1 through 4 don't actually synthesize ATP, but they're responsible for generating the proton gradient that does synthesize ATP. And again, that's in complex 5. So in this chapter, or in this lecture, we're going to learn the details of how complexes 1, 3, and 4 generate the proton gradient, and then the details from a structural standpoint for how complex 5, or this ATP synthase, is able to synthesize ATP. So part of our activities in class will walk through the details of this. So I'm just going to kind of do big picture overview of this. So again, complex 1, some of the big picture things. We've got NADH bringing electrons in, and they come in 2 at a time. So right at complex 1, we bring in 2 electrons, but the carriers that carry these electrons through only move protons 1 at a time. So we'll look a little bit at who those players are and how that works. How our proton gradient is generated is as we move these electrons between different redox carriers and they change their redox state, it causes a conformational change. And as we know, conformational changes can alter pKa's, and as we alter pKa's, we change whether residues are able to grab onto or release a proton. And in this way, we're going to grab protons from the matrix side and ultimately translocate them to the inner membrane space. So we're not going to go into too many details of that. Again, we'll look a couple structural details of some of the players, like FMN, which resembles FAD, coenzyme Q, again, which is this mobile carrier that's going to take the electrons after they've made their way through complex 1. And we'll see a lot of these Fe-S, which are iron sulfur clusters. So these basically have an iron 3+ that gets reduced to an iron 2+ as it takes on an electron, and toggling back and forth between those 2 redox states. But as we'll see as we move forward here, all of these carriers really, they might be able to carry at times 2 electrons at a time, but they take them on and give them up 1 at a time. And that's very different from NADH, which deals with electrons 2 at a time. Again, we'll talk a little bit more about this in class. You guys are not going to be responsible for knowing all of these details, but just understand that conformational changes change pKa's, and that can allow us to, in kind of a bucket brigade way, move protons from the matrix side all the way to the inner membrane space. Not too much to say about complex 2. Just remember that that is the citric acid cycle enzyme, succinate dehydrogenase, that converts succinate to fumarate. So it's actually part of the electron transport chain. Again, it delivers its electrons to coenzyme Q, very similar to how that happens in complex 1. But again, we don't have any proton translocation that occurs with complex 2, and so what this means is the only electrons that FADH2, or the electrons that FADH2 contribute, only pick up kind of value as they move forward. So that's why electrons from FADH2 are not worth as much as electrons from NADH. All right, third complex, and this is one we'll spend a good bit of time on an activity. I'm going to gloss over those slides as we kind of go through this overview here. Complex 3. And as we can see here, it looks like there's a number of arrows that we have here, and that's because we go through a cyclic process in the delivery of these electrons through complex 3. It's called the Q cycle. So we're going to deliver these electrons in such a way that we are twice as efficient in pumping our protons. Okay, so that is one thing that we'll spend a good bit of time in our activity going through, is how the Q cycle works. So I'm not going to spend any time really kind of talking about the details of it here. Just understand that it's a way that we have electrons kind of go through, and it's almost like you throw one electron up in the air. you run around to the other side and you grab it, and it allows you to have that electron kind of count twice. So we'll go through some of those details in our activity in class. So there's kind of two parts to the Q cycle. We'll also have an animation that can help us think about it. Again, a summary of that. That's all stuff that we'll deal with in our activity. But just remember, complex 3, the Q cycle is responsible for generating our proton gradient through that complex. And the reason we go through this Q cycle is it allows us to pump twice as many protons as we normally would have. Okay, complex 4, this is the end of the electron transport chain. Electrons ultimately get delivered to molecular oxygen at the end. And so in this way, we'll actually consider two kinds of protons that contribute to the proton gradient, because we will translocate protons, and we call those pumped or vectorial protons, ones that go from the matrix side all the way over to the inner membrane space. But we'll also have what we call chemical or scalar protons. These are protons that actually become part of a molecule. So again, when electrons get delivered to molecular oxygen, reducing it to make water, we grab two protons from the matrix side. So that indirectly helps contribute to the gradient, not by pumping protons to the other side, but by removing them from the matrix side to make molecular water. So again, we'll have activities that kind of walk us through chemistries in these different complexes. Most of our time will be spent with complex 3 and learning the Q cycle. But again, one thing that's really interesting to note here is we end up pumping 24 protons from the matrix side. But remember, only 20 of them actually get to the inner membrane space, because 4 of them end up with molecular oxygen as it gets reduced to water. So remember, electron transport is complexes 1 through 4. Complex 5 allows us to do oxidative phosphorylation, and that's where we utilize this proton gradient that we've generated to work this molecular machine, which we call an ATP synthase, and we synthesize ATP. You'll notice here it says ATPase, meaning it sounds like it's something that hydrolyzes ATP, and that's what this molecular machine wants to do. But if we give energy to it in the form of a proton gradient, we can get it to run in reverse and actually synthesize ATP. So that's the nuts and bolts of how that works. Not too much that I'm going to say as we go through these last few slides here, because we're going to get to the details for how this happens in our activity in class. Again, the idea is that if we want to couple these two processes, the proton gradient that's generated from the electrons from our fuels that were oxidized need to be directly coupled to the ATP synthesis machinery. If there's some other way that those protons can get back to the matrix side, we're not going to harvest that energy. So again, that intact inner mitochondrial membrane, that's what IMM stands for, is necessary. Don't worry about the math here, but this is an important equation that allows us to relate delta G, right? Delta G can be related to an equilibrium constant. So if we think about equilibrium constant being concentrations of two species on different sides, and if those concentrations of two species happen to be protons, we can actually relate the difference in pH to a thermodynamic parameter, free energy. And importantly, we can add this extra term here, which allows us to, in the case of mitochondria, give extra energy, extra thermodynamic value to this gradient, because it also builds up a charge gradient. Kind of remembering, coming back here, when we pump protons to this side, we generate a positive charge on the inner membrane space side of the inner mitochondrial membrane. And again, we're going to use that thermodynamic driving force to synthesize ATP. ATP is an endergonic process, so if we have some free energy that we can couple with that, that'll allow us to synthesize ATP. Don't worry about the numbers, don't even worry about remembering the equation. Just remember that it's a difference in pH and the ability to build up a charge. And that'll become important as we move into chloroplast activity in our next chapter. All right. Lot that we'll talk about in questions with our activity. Here is ATP synthase. And what I want you to remember is that we call it a lollipop protein, because if you think about it, it's got a lollipop head and then a stick that is attached to this part in the center, which is embedded in the lipid bilayer. So we're going to talk about these two different domains, The domain down here, which looks like a merry-go-round and so it looks like a circle, that is the F₁ domain. That's the domain that's responsible for translocating protons. So protons will kind of grab a seat in this merry-go-round and they will allow it to turn. We'll actually talk about how that turning process happens. But as that turning process happens, that molecular motion is translated up into this head group. And we have what's called a binding change. And so we kind of ratchet back and forth between different conformations that allow us to then synthesize ATP. So that's kind of what happens in a nutshell. We'll go through the details of how proton binding can cause this giant kind of molecular rotor to turn, and then ultimately how changes in conformations in this head group can synthesize ATP. So I'm going to skip over a number of slides here because we're going to get to the details of this in our activity. So we call this again a rotational motor because the rotation of this bottom domain as protons kind of come in and grab a seat on this merry-go-round allow us to have conformational changes imparted to the head group. And again, this head group is where we synthesize ATP. We'll have a really nice video that we can watch that kind of helps to illustrate this. This ratcheting is called a binding change mechanism. Okay? Stuff that we'll get to the details of in our activity, but ultimately what we have is 3 possible conformations, and those conformations we call loose, tight, and open. And different kinds of chemistry happens depending on whether you're in the loose, tight, or open conformation. And so we'll talk about how this process works, but ultimately that's how we synthesize ATP. So again, we'll summarize how this whole process works from movement of electrons to generate the proton gradient, dissipation of the proton gradient through this molecular machine, and that allows us to synthesize ATP. Again, we'll get into some details in our activity about how this physically can happen, and it really has to do with the fact that proton binding can induce conformational changes. And we thought about that almost a little bit in the reverse way with our electron transport, that if we have conformational changes, that can affect proton binding. So we're looking at it almost forcing it in the opposite direction, that we change the pH, we force something to be protonated, that causes a conformational change, and that physically moves that giant merry-go-round to turn it around. So really, really neat stuff. And at the very end, I have a cool video to show you kind of a proof of principle of this concept where we can actually, through a microscope, watch this molecular machine in action. Really cool stuff, electron transport and oxidative phosphorylation.